So in this video, I'll discuss the molecular orbital theory. So molecular orbital theory deals with symmetry-adapted linear combination of atomic orbitals. So sa VBT or sa ating valence bond theory, linear combination lang yung kinoconsider. Basta meron ka lang orbital overlap, nagkakaroon ka ng bond. Pero dito sa MOT or sa molecular orbital theory, i-consider natin yung symmetry. So ano ibig sabihin nun? I-consider na natin yung possible constructive and destructive interferences between orbital wave functions. Okay? So for example, we have orbitals 1 and 2, psi 1 and psi 2. Kapag ka nag-overlap sila, merong dalawang possible na results. Pwedeng constructive yung interference nila, which will form a bonding molecular orbital. Pwede ring destructive yung interference nila to form an antibonding molecular orbital. Okay? So that's how molecular orbital theory considers overlaps. So kino-consider niya equally yung probability, okay, ng constructive and destructive interference. So nangyayari constructive interference kapag ka in phase, okay, yung overlap. Kapag ka naman out of phase, yung overlap nyo, destructive naman yung interference na yun. So nagpo-form siya ng antibonding molecular orbital. Okay? So now let's look at the features of the molecular orbital model. So the amount of atomic orbitals should be equal to the amount of the resulting molecular orbitals. So makikita natin, may dalawa tayong atomic orbitals. So may result din siya na dalawang molecular orbitals. Okay? So ibig sabihin lang yan, every time na may orbital na nag-overlap, may equal possibility ng destructive at constructive interference. So yun ang ibig sabihin ng number 1. So number 2, the amount of bonding MO should be equal to the amount of antibonding molecular orbital. Okay? So, of course, equal sila kasi equal din yung probability ng constructive and destructive interferences. Okay? So, for number 3, the energy of the bonding molecular orbital should be less than that of the energy of the individual atomic orbitals. Kasi, ang effect ng ating bonding is stabilizing. Okay? So, ang unang principle natin pagdating sa bonding, nagre-release siya ng energy, yung bond formation energy. So, ibig sabihin dapat yung bonding orbital na to, mas mababa yung energy kaysa sa mga individual energies ng mga atomic orbitals na ito. Okay? So, the energy of the antibonding MO naman should be greater than the energy of the individual atomic orbitals. So, ang effect naman nito ay destabilizing. Okay? So, since destabilizing siya, mas mataas yung energy niya kaysa dun sa individual atomic orbitals. Okay? So, that's for the features of the molecular orbital model. So now, let's draw a molecular orbital diagram. So in this case, drawing natin yung molecular orbital diagram ng H2 molecule. Okay? So yung hydrogen, meron siyang electron configuration na 1s1. So ibig sabihin, yung 1s orbital lang yung occupied ng electron. So let's just consider the 1s overlap. Okay? So kapag kinonsider natin yon, the 1s orbitals, when they overlap, they form a sigma bond with the other 1s. So the name of your molecular orbital is sigma subscript 1s. So the 1s represents the orbitals that underwent the overlap. So ibig sabihin, that's the overlap or the sigma overlap between 1s orbitals. Okay? So kapag ka naman antibonding, okay, destructive interference, magkaiba yung phase ng ating orbitals. So lagyan nyo lang siya ng star. So that's sigma star 1s. That's the antibonding molecular orbital for the 1s sigma overlap. Okay? So ngayon, drawing na natin yung MO diagram ng H2. So yung molecular orbital diagram ng H2 ay nasa gitna, yung dalawang atomic orbitals ay nasa gilid. So mapapansin nyo, stabilizing yung effect ng ating molecular orbital. So nasa baba dapat yung ating sigma 1s, which is lower than the energies of both the 1s atomic orbitals. So dapat mas mababa yung energy niya kaysa dun sa dalawang 1s. Tapos dapat pantay yung dalawang 1s orbitals kasi equal lang sila ng energy. Okay? So yan ang ibig sabihin ng stabilizing effect ng bonding orbital or bonding molecular orbital. So kapag ka antibonding naman, dapat mas mataas siya dun sa dalawang 1s. Okay? So meron na tayong molecular orbital for the hydrogen molecule. So that's the sigma 1s bonding orbital and the sigma 1s antibonding orbital or the sigma star 1s. So since tig-isa lang yung electron nila, ang nasa molecular orbital mo ay dalawang electrons lang. So ilalagay nyo muna siya sa mas mababang energy bago sa mas mataas na energy. So if-follow nyo dito both yung Aufbau and the Hund's rules. Okay? So i-follow nyo to tuwing nag-fill out kayo ng molecular orbital diagram. Okay? So kapag dinrawing nyo yung molecular orbital diagram, may dalawang electrons doon sa sigma 1s at walang electrons doon sa sigma star 1s kasi dalawa lang yung ating hydrogen electrons. Okay? So finally, we will calculate the so-called bond order. So the formula for the bond order is 1/2 times the number of electrons in the bonding molecular orbital minus the number of electrons in the antibonding molecular orbital. So for hydrogen, we have 1/2 times 2 electrons in the bonding molecular orbital minus 0 dun sa ating antibonding molecular orbital. We have 1 for the bond order. So therefore, hydrogen has 1 bond. Kaya ganito yung Lewis structure ng ating hydrogen. Okay? So for the next example, draw the molecular orbital diagram for helium-2. So helium-2 is 2 helium atoms with an electron configuration of 1s2. Okay, so 1s lang yung ating occupied na atomic orbital. So letter A, determine the possible overlap between the 1s orbitals. We already did this. So meron tayong sigma 1s and sigma star 1s. Okay? So next is to draw the molecular orbital diagram for helium-2. So since tig-dalawa naman sila, okay, mafi-fill out natin pareho yung bonding and antibonding molecular orbitals. So this is the molecular orbital diagram for helium-2. So ngayon, i-calculate natin yung bond order. So for the bond order, again, it's 1/2 times the number of electrons in the bonding molecular orbital minus the number of electrons in the antibonding molecular orbital. So for helium, that's 1/2 times 2 minus 2, that's 0. So ang ibig sabihin ng 0 na bond order, helium-2 is too unstable to form. So therefore, wala tayong helium-2 na molecule. Okay? So based from this example, the molecular orbital theory can also predict if a certain molecule can form or not. Okay? So it's based on the bond order. So kapag 0 yung bond order, it does not form. Kapag non-zero yung inyong bond order, it is possible na pwede mag-form yung inyong molecule. Okay? So for example, we can say that helium plus may form because of its molecular orbital diagram and the bond order of 0.5. Although yung 0.5, it's kind of a weak type of bond kasi 0.5 lang ibig sabihin yung bond na to, hindi siya single bond, hindi siya mako-consider as one bond kasi ang bond order niya ay hindi 1, 0.5 lang. Okay, so mas mahina siya sa typical na single bond. Okay, so by observing the behavior of molecular orbitals, we will realize that atoms with closed shell configurations do not form diatomic molecules. So for example, we have beryllium-2. So yung beryllium-2, that's 2s2. Okay, so ibig sabihin meron siyang bonding sa 1s niya and sa 2s orbitals. Okay? So since yung 1s niya ay 1s2 per beryllium atom, magkakaroon tayo ng 4 na electrons doon sa 1s, sa sigma 1s and sa sigma star 1s. So tigdalawa sila ng electrons. Okay? So yung 2s din natin ay may tigdalawa per beryllium atom. So tigdalawa din yung electrons doon sa sigma 2s at sigma star 2s. So ibig sabihin, ang bond order niya ay 0. So ibig sabihin, ang ating beryllium-2 ay too unstable to form. So, ganun din yung neon-2. Okay? Ganun din yung argon-2. So, lahat to hindi nagpo-form kasi closed shell configurations yung mga orbitals nila. Okay? So, for this next example, i-consider na natin yung mga bonding hindi lang sa s orbitals, pati na rin sa p orbitals. So, in this example, let's draw the molecular orbital diagram for the oxygen molecule, O2. So, the electronic configuration of oxygen is 1s2, 2s2, and 2p4. So, ibig sabihin, meron siyang 1s orbital, 2s orbital, and the 3 2p orbitals in the 2p subshell. Okay? So, possible orbital overlaps for 1s, meron tayong sigma 1s and sigma star 1s. So, sa 2s, we have sigma 2s and sigma star 2s. Okay? So, puro sigma bonds lang sa ating mga s orbitals. So pagdating sa 2p, i-consider na natin yung mga orientations ng ating mga p orbitals. Although we have to keep in mind na yung 2px, 2py, and 2pz, pare-pareho sila ng energy. Magkakaiba lang sila ng orientation. So ang tawag doon ay mga degenerate orbitals. So kapag degenerate ang orbitals, pare-pareho sila ng energy, ang pinagkaiba lang nila ay orientation. Okay? So sa 2px, ang orientation niya with respect to this axis is like this. Okay? So kapag ka nag-overlap yung dalawang orbitals na yan, pwede tayong magkaroon ng positive overlap. So this is the sigma 2px kasi sigma bond yan. So pwede rin tayong magkaroon ng negative overlap. So yung negative at positive nag-overlap. So magkakaroon ng destructive interference. So that's the sigma star 2px. Okay? So walang nodes dun sa internuclear line. So this is sigma bond ng 2p orbital. So pwede rin natin siyang tawaging sigma 2p and sigma star 2p. Okay? Kasi yan lang naman yung orbital na nag-overlap through sigma bond. Okay? So, pwede rin natin siyang tawagin like that to generalize the sigma bonding between 2p orbitals. So, kapag ka naman 2py, makikita natin na yung 2py ay ganito yung orientation. Okay? So, sa dalawang atom, ganyan yung magiging overlap ng inyong 2py kapag naka-align sila sa isa't isa. So, magkakaroon ka ng pi bonding. Okay? So, ito yung pi bonding na positive ang overlap. This is the pi bonding na negative yung overlap. So, therefore, this is the pi 2py and this is the pi star 2py. Okay? So, pi bonding kasi meron tayong node dun sa ating internuclear line. Okay? Actually, pag ganito yan. Okay? So, pwede tayo mag-drawing dyan ng plane, okay, yung nodal plane na tinatawag. So that's a pi bonding. So ganun din sa 2pz, okay? So sa 2pz nag-overlap yung kanilang mga lobes dun sa kanilang 2pz orbitals. So meron din siyang nodes, okay? Or one node at least. Okay? So yung node na yan ay nodal plane. So kapag ka positive ang overlap, that's pi 2pz, and then kapag negative ang overlap, that's pi star 2pz. So 2py and 2pz are both pi bonds. So ibig sabihin parehong-pareho lang sila ng energy ng molecular orbital. So pwede natin siyang i-generalize as pi 2p and pi star 2p. Pero may tig-dalawa silang molecular orbitals. Okay? So dalawang orbitals for the pi 2p, dalawang orbitals din for the pi star 2p. Okay? So now, we can draw the molecular orbital diagram. Okay? So, dinawin nga natin yung 1s and 1s na and 2s na orbitals. Okay? So, meron tayong sigma 1s and sigma star 1s for the 1s orbitals. Meron tayong sigma 2s and sigma star 2s for the overlap of 2s orbitals. So, syempre, mas strong ang sigma bond ng 2p kaysa sa pi bond niya. So, nasa baba yung sigma bond ng 2p, or this is the sigma 2px. Okay? So, pwede rin natin siyang tawagin na sigma 2p. Okay? So, dito naman, okay, this is the pi bond. So, pareho sila ng energy, pero dalawa sila. Kasi, one is for the 2py and one is for the 2pz overlap. So, that's pi 2py and pi 2pz. Overall, pwede rin natin siyang tawagin na pi 2p, okay, yung buong molecular orbital na yan. So, may dalawa siyang orbitals na pareho ng energy. So, syempre, yung kapag ka mas mataas ang overlap degree, mas malakas din or mas unstable din yung kanilang yung antibonding molecular orbital. Since mas mataas ang degree ng overlap ng sigma kaysa sa pi, mas mataas yung energy ng antibonding ng sigma kaysa sa pi. Ibig sabihin, mas destabilizing yung sigma antibonding kaysa sa pi antibonding kasi mas mataas yung degree ng overlap. Okay, mas mataas yung degree ng destructive interference. Okay? So, therefore we have here the pi star 2p, pwede natin silang tawagin collectively as the pi star 2p, and this is the sigma star 2p. Okay? So, yan na yung molecular orbital diagram for the oxygen. So, kailangan lang natin punuin sila ng electrons. So, since ang ating oxygen ay may tig-8, so that's 16 electrons. So, that's 2, 4, 6, 8, 10, 12, 14. Tapos, yung dalawa, it should follow Hund's rule. So, 15, 16. Okay? So, that's for the molecular orbital diagram of oxygen. So, ganito magsulat ng molecular orbital diagram. Okay? So, computing the bond order, we have 10 electrons sa ating bonding molecular orbital, 6 electrons naman sa antibonding molecular orbital. We have 10 minus 6, that's 4 divided by 2, that's 2. So, therefore, yung Lewis structure natin ng oxygen is containing a double bond. Okay? So, check natin. So, for the bonding molecular orbitals, 2, 4, 6, 8, and 10. So, kapag ka naman sa antibonding, 2, 4, 6. Okay? So, that's for oxygen. Okay? So, after constructing the molecular orbital, tingnan naman natin yung kanilang mga features. So, for number 1, properties of the molecule can be explained by the HOMO and the LUMO of the molecular orbital diagram. So, what are HOMO and LUMO? So, HOMO is the highest occupied molecular orbital. So, yun yung orbital na may pinakamataas na energy at occupied ng electrons. So, in case of the oxygen molecule, ito yung HOMO. That's the pi star 2p or the pi star 2py and the pi star 2pz. Okay? So, ano naman yung LUMO? The LUMO is the lowest unoccupied molecular orbital. So, yung LUMO ay nasa itaas lamang ng inyong HOMO. So, siya yung susunod na orbital after the highest occupied molecular orbital. So, the LUMO is the sigma star 2p or the sigma star 2px. Okay? So, sinasabi ng mga orbitals na yan kung ano yung magiging reactivity ng inyong oxygen molecule. So, nandito na rin ang bond order, which is 2. Okay? So, yung inyong bond order, yung inyong HOMO and LUMO, meron na kayong particular properties na madederive from there. So, since anti-bonding yung HOMO, ibig sabihin, destabilize yung mga electrons na nasa HOMO. Ibig sabihin, hindi sila ganun ka-stable sa molecule. So, Yan, ito yung statement. Antibonding molecular orbitals are unstable molecular orbitals. So therefore, electrons in the antibonding HOMO, okay, so yung ating highest occupied molecular orbital, tend to be donated. So kapag ka sa isang chemical reaction, yung oxygen yung nagdo-donate ng electrons. Okay, so may mga tawag tayo dyan. Pwede natin siyang tawaging nucleophile, pwede din natin siyang tawaging Lewis base, etc. So maraming versions, depende dun sa type ng reaction na kinoconsider natin. So overall, oxygen tends to donate its electrons or act as an electron donor kapag dating sa mga iba't ibang reactions. Okay? So, yan yung makikita or mape-predict natin from the HOMO kasi ang HOMO niya ay antibonding. So, another, okay, is that oxygen is paramagnetic. Since meron tayong unpaired electrons dun sa HOMO, it means that the oxygen molecule is paramagnetic. It interacts with a magnetic field. Okay? So another feature of your molecular orbital diagram is that it can illustrate the so-called sp mixing. So sp mixing is a phenomenon that occurs for molecules with electrons that are less than or equal to 14. So kapag less than or equal to 14 yung electrons ng inyong molecule, nagkakaroon siya ng sp mixing. So ano yung sp mixing? Since yung mga molecules na ganito karami lang ang electron, they tend to have low values of the effective nuclear charge, yung s at p orbitals nila masyado nang magkalapit yung energy. So, the s and the p orbitals mix in the n equals to subshell or the n equals to principal quantum number. So, meaning the 2s and the 2p. So, by mixing, ang nangyayari, na-destabilize yung ating sigma 2p. Okay? Tapos, nai-stabilize naman yung mga pi 2p. So, nagpapalit sila ng energies or nagsuswitch sila ng energies. Okay? Mas nai-stabilize yung pi bonding kaysa sa sigma bonding. Okay? So, the pi 2p orbitals become more stable than the sigma 2p orbitals. The positions in the MO are switched due to sp mixing between the 2s and the 2p orbitals brought about by the low z effective of the centers of your molecule. Okay? So, the HOMO of B2 is partially filled. So, makikita natin dito, yung HOMO ay yung pi 2p. Okay? Tapos, yung LUMO ay sigma 2p or the sigma 2px. So, partially filled bonding MO yung HOMO ng B2. The LUMO is also a bonding orbital. So, ibig sabihin, hindi puno yung mga bonding orbitals ng ating boron 2. So, ano ibig sabihin nun? Since B2 lacks electrons in the bonding orbitals, it tends to accept electrons. So, kapag ka sa chemical reaction, siya yung tumatanggap ng mga electrons para mapuno niya yung kanyang mga bonding orbitals. Okay? So, yun yung mga properties na pwede nating ma-predict sa molecular orbital theory. Yung tendency to accept or donate electrons, okay? So kapag ka naman accept electrons, this can be called an electrophilic, okay, compound or Lewis acid. So depende yan sa type of reaction na kino-consider natin. So B2 is also paramagnetic kasi unpaired yung mga electrons niya sa HOMO. Okay? So here we have another example, nitrogen. So nitrogen has a HOMO of sigma 2p. So here is sigma 2p or the sigma 2px, and the LUMO is the pi star 2p, which is here. Okay, ito yung kanyang LUMO. So the pi star 2p it also can be called pi star 2px and pi star 2py. So degenerate ang mga molecular orbitals na yan. So the bond order for nitrogen is 1/2 times 10. So yung 10 ay 2, 4, 6, 8, 10. Okay? Tapos 4 antibonding electrons, so 2, 4. So that's 10 minus 4 is 6 over 2, that's 3. So therefore, the Lewis structure of your nitrogen contains a triple bond. Okay? That designates the bond order. So, yung nitrogen nyo ay may sp mixing kasi yung total number of electrons niya ay 14 lang. So that's 7 plus 7 for each nitrogen. So the HOMO is a fully filled bonding MO and the LUMO is an anti-bonding orbital. So since fully filled na yung bonding orbitals ng inyong N2 and wala siyang orbital sa anti-bonding, N2 is a very stable and inert molecule. Wala siyang tendency to donate or accept electrons. Kasi kapag nag-accept siya, mapupunta yun sa anti-bonding. Kapag nag-donate naman siya, mawawalan siya ng electron sa bonding orbital. So, ang N2, it's very stable. Hindi na siya nagre-react through electron donation or electron acceptance. Okay? So, also, N2 is diamagnetic kasi wala tayong makikitang unpaired electrons sa kanyang molecular orbital diagram. Okay? Another feature of your molecular orbital diagrams is that it can compare energies between atoms. So, kanina yung mga examples natin ay puro homonuclear diatomics. Ibig sabihin, yung mga atoms ay identical dun sa molecule. Okay? So, ganito yung nakikita nating molecular orbital. So, pareho lang yung energies ng 2p, 2s, tsaka 1s ng ating mga atoms. So, therefore, ganito yung itsura ng nagiging resulting nating molecular orbital. Pero kapag ka naman heteronuclear diatomic, ganito yung naging itsura. So, nagkakaroon ka ng difference in the energies of the two atoms. Siyempre, yung more electronegative atom, siya yung mas mababa yung mga energies. Okay, yung mga atomic orbital energies. So, mas mataas yung atomic orbital energies ng mga atoms na mas mababa ang Z-effective or less electronegative atoms. Okay? So here we have some examples. So for the first one, we have the nitrogen monoxide. So for the nitrogen monoxide, makikita natin na yung mga atomic orbitals ng nitrogen ay mas mataas kaysa doon sa inyong oxygen atomic orbitals. Kasi mas electronegative si oxygen kaysa kay nitrogen. So, makikita nyo din dito na they have a total of 15 electrons. So that's 2, 4, 6, 8, 10, 12, 14, and 15. So nag-iisa lang yung electron dun sa ating antibonding orbital. Okay? So pag kinalculate nyo yung bond order niya, that's 1/2 times, so bonding electrons muna, 2, 4, 6, 8, 10. So 10 minus yung antibonding ay 2, 4, 5. 5. So ang kanyang bond order ay 2.5. Okay? So for the next example, we have the cyanide. So makikita natin na yung mga atomic orbitals ng inyong carbon ay mas mataas kaysa doon sa nitrogen naman. Since CN contains only, so yung inyong carbon ay may 6, okay? Tapos yung inyong nitrogen ay 7, so that's 13 electrons. Meron siyang sp mixing. Okay? So for the bond order, we could calculate that's 1/2 times 2, 4, 6, 8, 10. So 10 bonding electrons, tapos 2, 4. So 4 antibonding electrons. So 10 minus 4 is 6. 6 over 2 is 3. So ang Lewis structure ng ating cyanide ay C triple bond N. Okay? So ganyan. Minus. Okay? So may triple bond tayo dahil yung ating bond order ay 3. So finally, for the binary halo acids like HF, HCl, HBr, and HI, okay, pare-pareho lang sila ng pattern pagdating sa molecular orbital structure. So for example, for HF, since sobrang electronegative ng fluorine compared sa hydrogen, hindi na nag-i-interact yung hydrogen 1s orbital sa s orbitals ng F. Nag-i-interact na siya sa p orbitals. Okay? Tsaka yung p orbitals kasi yung outermost shell ng ating fluorine. So hindi siya makakapasok dun sa mga inner orbitals. Okay? So the electronegativity of F is far greater than that of H. That is why the 1s orbital of H interacts with the 2px of F. So sobrang tightly held na kasi ng 2s and 1s, kaya nasa pinakaloob na siya ng inyong fluorine. So yung 1s ng hydrogen, nakakapag-interact na lang siya dun sa mga orbitals dun sa n equals 2 subshells, or yung 2s and 2p subshells. Okay? So ito lang yung interaction. So makikita natin na meron tayong bonding molecular orbital between the s and the p, and meron din tayong antibonding orbital as well. So makikita natin dito, meron tayong sigma and sigma star. Okay? So yung 2py at 2pz, hindi sila makakapag-bond sa s orbital kasi magkakaroon ka ng net zero na interference kasi kalahati ay constructive, kalahati ay destructive. So malalaman nyo yan kapag pumunta kayo sa higher chem. Makikita nyo na destructive ang net interference ng inyong PZ at PY orbital tsaka yung 1s orbital. Okay? Hindi sila compatible ng symmetry. Ang compatible lang sa symmetry ng s orbital nyo ay yung 2px. Okay? This is why nakakapag sigma bond sila. So hindi capable din yung s orbital for pi overlap, so hindi siya nag-interact with the 2pz and 2py. Okay? So therefore we have this particular molecular orbital diagram. So itong mga nasa box na ito, okay, itong 2s na to, tsaka yung 2py at 2pz, they are called non-bonding electrons. Okay? So yung non-bonding electrons, magmamanifest yan sa structure ng ating HF. So makikita nyo meron siyang 6 na electrons dyan, or 3 lone pairs. Okay? Since ang bond order niya ay 1 kasi isang bond lang naman ang nagawa niya dyan, isang sigma bond ang nagawa niya. Okay? So single bond yung inyong HF. Okay? So this is my discussion on the molecular orbital theory. So for the next discussions, i-discuss ko na yung orbital hybridization specifically for carbon. Tapos mag-introduce na ako ng organic compound structures. Okay? So see you next video.